Hello, statisticians! Mr. Youngsaver here from Skew the Script. We have a fun topic to discuss today, Moneyball. Let's skew it! Today's lesson's on describing a quantitative variable. Let's jump in. Moneyball is a movie about the Oakland Athletics baseball team, also known as the Oakland A's, and their 2002 season. When the movie came out, it was a big hit. At the box office, it grossed $110 million.
Come on!
However, the wide popularity of the movie about the Oakland A's 2002 season is a bit of a surprise because in 2002 in the major leagues, it wasn't the A's, but the Yankees that scored the most runs. It wasn't the A's, but the Braves that had the largest division lead at the end of the season. It wasn't the A's, but the Angels that won the championship at the very end. So that brings us to today's key question. Why would anyone make or even watch a movie about the Oakland A's? With that question in mind, let's move into our guided notes. We're going to discuss 4 topics today, starting with dot plots. To get a sense of the movie Moneyball, let's watch my favorite scene featuring Brad Pitt playing the general manager of the Oakland A's.
No, what's the problem, Barry?
We need 38 home runs, 120 RBIs, and 47 doubles to replace.
The problem we're trying to solve is that there are rich teams and there are poor teams. Then there's 50 feet of crap. And then there's us.
As the clip makes clear, in professional baseball, there are rich teams and there are poor teams. This table shows all team payrolls from that 2002 season. The payroll for a team is the total amount of money they paid at players, and the payroll, measured in dollars, is a quantitative or numerical variable. The New York Yankees had the highest payroll at $126 million. This means they could pay to get players that were star players. But the Oakland A's, on the other hand, had the third lowest payroll at $40 million. With a lower payroll, it's more difficult to attract star talent. We could take this data and construct a dot plot. The dots show the payrolls of all the different teams, and the teams with highly similar payrolls get stacked on top of each other. The New York Yankees are represented by this dot at $126 million payroll. The Oakland A's and Minnesota Twins, who both had a $40 million payroll, are here and they're stacked on top of each other. One advantage to using a dot plot is that we get to see every data value as its own dot, laid out on the full scale of the data. This is especially useful for smaller data sets like this one. A couple of disadvantages are that we can't see each point's exact value. If a dot falls between those tick marks on our scale, we have to slightly eyeball and estimate its exact value on the x-axis. And another disadvantage is that because every data value gets its own point, dot plots can be a bit overwhelming to look at for very large data sets, making patterns hard to see. If there were a ton of dots here, it could be hard to see the patterns among them. The first disadvantage brings up a question. How can we visualize every data point's exact value? That brings us to the next type of quantitative variable graph that we're going to look at, stem and leaf plots. To make a stem and leaf plot, we first have to figure out how we'd like to group our data. We see that we have 2 teams with payrolls in the $30 million range. We have 7 teams with payrolls in the $40 million range. We have 5 teams in the $50 million range, and so forth. So what we can do is put the teams into groups of tens of millions of dollars, starting from 30 million to 40 million, all the way up to 120 million. We call these groupings the stems. Think of them like the stem on a plant. And from the stem, we extend the leaves, or the individual values of each team. For example, the Tampa Bay Rays had the lowest payroll at $34 million. We can represent this payroll using the $30 million stem and giving the Rays a leaf of 4. Together, this stem of 30 and leaf of 4 represent $34 million, or the Rays payroll. Because the Expos had a payroll of $39 million, we can represent them with a leaf of 9 in the stem of 30. Because the A's had a $40 million payroll, they moved to the 40 million stem and they have a leaf of 0. Same thing with the Twins, who also had a $40 million payroll, and we proceed through the rest to make our full plot. Note that if you're asked to make one of these plots in the AP exam, you should always make sure to include both a title and a key. A key is especially important for stem and leaf plots. The key advantage of a stem and leaf plot is that you get to see the exact values of every data point in ways that might be a little bit more difficult in a dot plot or other kinds of plots. However, a disadvantage is, again, that they can be a bit overwhelming to look at for larger data sets. So this raises the question, what is a good data visual for larger data sets? And that brings us to the final graph we'll discuss today, histograms. Let's see if we can summarize this data even more compactly. To do so, we're going to organize the data values into intervals called bins. Note that it's fairly standard for these intervals to include a lower bound, hence the less than or equal to sign, and it's fairly standard for these intervals to exclude their upper bounds, hence the less than signs without the equal to notation. We see that there are two teams in our data set that fit in the first bin. Note that the A's with a $40 million payroll do not go into this bin, since that upper bound of 40 million is excluded from this bin. Instead, they'll go into the next one, where there are 12 teams. And we can fill in the rest for a total of all 30 teams captured from our data set. And it's worth noting that only one team had a payroll in that highest interval, the New York Yankees. Using our table, we can now construct a histogram. We're going to use the x-axis to represent the variable we're measuring, the payrolls, and we're going to use the y-axis to represent the frequency of different payroll values. When we do this, this is what we get, a visualization of these bins known as a histogram. You might notice that it's somewhat similar to a bar graph. However, unlike a bar graph, there are no spaces between the bars, indicating that we're visualizing a quantitative variable rather than a variable with distinct categories. The best way to read a histogram is to look at the bar heights. For example, we see that the 80 to almost $100 million bin has a height of 4. This means that 4 teams had a payroll in that interval. It's important to note that the height of the bar doesn't indicate that these teams have a higher or lower payroll. In fact, the highest payroll team, the Yankees, are represented by the bar with the lowest height. The height of the bar merely represents the number of data values or the frequency of data values in a certain interval or bin. In this case, only one team, the Yankees, fit in that very high bin of $120 million and above. In addition to looking at the frequencies of data values in these bins, we can also look at the relative frequencies or proportions. For example, we can see there are 2 teams with payrolls between $20 and almost $40 million out of a total of 30. We can represent the relative frequency by dividing 2 out of 30, which yields a proportion of 0.067. Converted to a percentage, this is 6.7%. So 6.7% of teams have payrolls between $20 and almost $40 million. Similarly, there are 12 teams in the next bin. Out of 30 total, this is a proportion of 0.40 or 40%. So 40% of teams have payrolls between $40 million and almost $60 million. And then we can do the same for the rest. Note that the relative frequencies, since we're using relative frequencies, the total is 100% or all the teams. We can take these relative frequencies and construct a relative frequency histogram. Looks basically the same way as the raw frequency histogram we did earlier, but now the y-axis is the percent or relative frequency. So the bar heights tell you the percent of the data set contained within a certain bin. The key advantage of histograms is that they're great for summarizing large data sets, as the bins help you group the data, making patterns easier to see. However, the largest disadvantage is that you can't now see the individual data values at all. And instead, you can only see an interval that contains those values. Finally, let's talk about describing a distribution of data. And this may come as a surprise to you, but in statistics class, we ask you to cuss. Yes, that's right. We ask you to cuss in class. And all that we ask is that you make sure to cuss with context. What do we mean by this? Well, it means that you'll sometimes be asked to describe the center, unusual features, shape, or spread of a quantitative distribution, or CUS for short. And when you're asked to describe these features, you always want to make sure to include context. For example, here's that histogram of team payrolls. So you may be asked to describe the center of a graph like this. The central value of this distribution, or the middling value, appears to be between $60 and almost $80 million. Note that this is just a visual estimate of the central values of this distribution. In a later lesson, we'll learn how to calculate more specific measures of center, such as means and medians. So that's what we'd write in our response. The distribution of team payrolls is centered between $60 million and almost $80 million. Note that in my response, I made sure to mention context by including the name of the variable, team payrolls. You want to do that in all descriptions of features of graphs. Next, you may be asked whether there are any unusual features in the distribution. To see what unusual features could look like, imagine that the distribution actually looked like this instead. So one unusual feature of this version of the graph would be that there's a gap between 80 to almost $120 million. The other unusual feature would be that this highest paying team is a potential outlier, as its payroll is unusually high compared to the rest of the data set. However, our graph actually looked like this. As you can see, there's no gap there, and that highest paying team is no longer an unusually high amount compared to the rest. So it's likely not an outlier. So we could respond that there do not appear to be any gaps or outliers, and therefore no unusual features are visible for our graph. You may also be asked to discuss the shape of a distribution. Let's discuss what we mean by shape. When describing shape, you can comment on the number of modes or peaks. If a distribution has 0 prominent peaks or modes, we'd say it's approximately uniform, meaning that the frequencies are uniform or similar across data values. If a distribution has 1 clear peak or mode, we say it's unimodal. Finally, a bimodal graph has 2 distinct peaks or modes. Another important aspect of shape to describe is symmetry or skew. If a distribution has a tail on the left, it's called a left skew or negative skew. A tail on the right indicates a right skew or positive skew. And a distribution in which the sides are roughly a mirror image of one another is considered roughly symmetric. Now, you may have noticed that the word skew appears in the name of our organization, Skew the Script. This is no accident. As educators, we notice that when we use the usual script of teaching math and statistics with irrelevant examples, such as Bob having 58 watermelons or calculating the mean lifetime of batteries, students' scores look like this, a right skew. Many low scores on the left and only a few high scores on the right. However, when we went off script and used math and stats to explore genuinely relevant topics that students cared a lot about, students engaged more in class and they performed better as well. As a result, their scores became a left skew, very few low scores on the left and many high scores on the right. That's why this left skew curve appears in our logo. It's a symbol of what we hope to accomplish by bringing more genuinely relevant examples to math and statistics classrooms. So we can draw a line above the frequencies on our graph to get a better sense of its shape. And this line makes it clear that the distribution of team payrolls is right skew with the tail on the right. It's also unimodal with just 1 prominent peak. Finally, you may be asked to describe the spread of a distribution. We see that these data values vary from the low end of $20 to almost $40 million up to the high end of $120 to almost $140 million. So we'd say in our response that the team payrolls vary between those intervals. Now that we've done so much work with this data, let's get back to our key question. Why would anyone make or watch a movie about the Oakland A's? As we saw before, the A's had a much lower payroll than wealthier teams such as the Yankees. To make up for this deficit, the A's had to develop a strategy. And that strategy is best explained by my second favorite scene from the movie, which we'll play now.
It's about getting things down to one number. Using stats the way we read them, we'll find value in players that nobody else can see. People are overlooked for a variety of biased reasons and perceived flaws. Age, appearance, personality. Bill James and mathematics cut straight through that. Billy, of the 20,000 notable players for us to consider, I believe that there's a championship team of 25 people that we could afford, because everyone else in baseball undervalues them. Like an island of misfit toys.
The A's were one of the first teams to use advanced statistics to identify undervalued players. In other words, effective players that they could afford. The result was that even though the distribution of team payrolls looked like this, the distribution of wins per team looked like this. The Yankees, as you may expect, won an impressive 103 games by the end of the season. However, the Oakland A's, with their payrolls being a fraction of the Yankees, also had 103 wins. They somehow tied the Yankees to have the best record in baseball that season. To put this in perspective, this means that with their payrolls, the Yankees spent about $1.2 million per win, over $1 million per win. Meanwhile, the A's from Oakland only spent $0.4 million per win. A very impressive feat. That brings us to our discussion for the day. Major League Baseball has what's called a luxury tax. Rich teams pay a tax to the league, and the revenue is used by the league to help fund poorer teams. However, the poorer teams say that the tax isn't big enough to make much of a difference. Imagine the league enacted a harsher and bigger tax in the 2002 season, the same season from the movie and where we have this data from. Any money spent above $100 million on payroll is taxed at a 90% rate. So 90% of that money is taken by the league and given to poorer teams. This leads us to two discussion questions. A, how would this change the distribution of team payrolls? Comment on center, shape, and spread. And B, in your opinion, would this new system be better for the sport? Why or why not? Take a moment to jot down your initial thoughts of these questions, and we'll discuss them further in class. That's it for today's statisticians. We'll see you next time.